Our next speaker is Marius Junge from Urbana-Champaign. His title, Entropy, Decay in Large Open Systems.
Right. So the good news is I can come a little bit closer so that I can follow what you are seeing on the screen. So this is joint work with my students, Haojian Li, LaRacuente, and the last part is with Yidong Chen. I want to thank Arthur for two things. First of all, for combining this melting pot of different ideas. This is wonderful. Also, the previous speaker talked about hypercontractivity. Essentially, in a nutshell, we tried to use hypercontractivity forever, and we failed. I mean, it's still in the same spirit, but it tells you, what we couldn't do. So there's the classical background. I would have spent half an hour doing it. So thank you, Arthur. Thanks the previous speaker. So this is what reminds me of this. So a little bit about motivation. So for the operator algebra people, this is this kind of funny thing. There is actually a physical motivation, which I learned. And then so there are words like open system, Rydberg distance, photon emission, which, I first saw that I said, okay, this is fantasy, sci-fi. But actually, I mean, I think there's probably a little bit more than sci-fi. This really has to do with some of the things I'm interested in. In particular, my starting point is this Lindbladian, right? So we are talking about a matrix algebra. So X is a matrix, L is a superoperator, and Lindblad in 76 characterized all generators of family of maps, which are completely positive unidimensional maps on matrix algebras. So I'm not insisting that everybody here knows exactly what a completely positive map is. Some of you certainly do, but it's a family of nice maps, which if you combine them with another system, preserve positivity. That's essentially the message we want. For that characterization, the thing you have to understand that this acts for X are observables. That's the thing you have to understand, right? And AJ are just really matrices, so it's very elementary. But what I learned later is that you split up the first part in front of the two, you call it psi of x, and the rest you call it h star x minus xh. Because if you want to write down some kind of evolution, the right part is easy to write down. So every Lindbladian splits into two parts, a map psi, which is given by aj star xaj. I'm a mathematician, so star is dagger, right? So I mean, for those who have not seen this before. So the first thing is obviously what we call completely positive, because, multiplying with a star a preserves positivity. And this psi of x is, that is a completely positive, not unital map, and it has an interpretation. I did out two interpretations for you. So there's this quantity which I learned to accept as a quantity of relevance. We take psi squared of 1 is an observable, that makes sense. We take a density, so we are applying psi squared to a density, to a state, and we do divide this by the square of doing it once. This looks like some kind of covariance, right? And so if this G2 is bigger than 1, it's called bunched light. Equal to 1, it's coherent light, and less than 1, it's anti-bunched light, and that is a way to measure whether you have non-class. If G2 is less than 1, this is called non-classical light. So from a mathematician, you have this completely positive map. You evaluate this at 1, you get a number, you do some little operations, and suddenly this has a meaning. What is super fascinating is that this photon emission number, which corresponds to trace rho psi of 1, so you're measuring in a certain state how many photons have been emitted, right? This number can actually be measured. I mean, it's not easy. I mean, starting from 2000, I think, they were able to measure this physically and count it, right? So there's a connection of these Lindbladian for open systems, and there are some parameters for these Lindbladians which seem to have, from what I see, in optics, they have a meaning, and they have been studied for quite a while. So that's kind of motivation why Lindbladians should not be completely ignored. They are not so popular in the quantum, in the computer science part, but completely positive maps, I think, for me, are okay. So here we go. I brought you a picture for this, which has essentially where this is coming from. You have a bunch of atoms in such an array. You have electric field, you put it on, then you stop it, and they start to emit photons, and you measure the number of photons they emit, and depending on the distance, they interact or they don't interact, right? So this is something I took from a paper by Anziger. So these are physical configurations which I claim are relevant for our analysis. Now I'm turning to a systematic question of what is decay, right? I mean, Lindbladians are supposed to describe noise. You have some noise in the system. You might have seen here before the h part, right? You see this little h there. H is a unitary evolution. If you exponentiate that, you get really conjugation by a unitary. That does not destroy information. That's a unitary evolution that leaves a state invariant. But the rest is noise. So we are talking about noise models for open quantum systems. And then we have to ask, does the noise give some kind of decay, right? So you expect that if you start like in a heat semigroup, you start in a certain initial position. After some while, you will go to the equilibrium situation. That's what we expect to happen. And now we are measuring how fast and in which quantity this happens. So if you have your L, we are talking about matrices. We can define the energy between x and y as trace of L x star y. So spectral gap means if L of x is 0, then the 2 norm is less than the energy norm, and you have a constant. And if this constant lambda 2 works for all x, we call this the spectral gap. That's actually super standard in all the fields I've worked so far, right? So that's called spectral gap. The next measure of decay is the logarithmic Sobolev inequality. So I'm giving here a shortcut because I'm not explaining why that is important and where the Sobolev inequalities are coming from. But mathematically, it's pretty easy. You have a semi-group. Semi-group means that e to the TL times e to the SL is e to the T plus SL, right? Semi-group property. You go to the limit, and then you calculate the relative entropy of X versus P infinity of X, and you want to compare to the energy. So what my previous speaker did not tell you is that if you differentiate these interesting P to Q inequalities, you end up exactly with this expression. Yeah, so it's a differentiation, and it's very well known that this is a two-way street, right? I mean, you can go from hypercontractivity to this inequality and back, and you know, I think it's really fair to say that this is super well understood in many situations, right? So then there is this modification I have to go to, which is called modified logarithmic Sobolev inequality, where we just modify it a little bit. We keep the left-hand side, and we replace the energy form by energy of x log x. So why do we do that? It's actually a good question. It was observed that for discrete system, this inequality is a little bit more stable. Log Sobolev inequality implies this inequality. And here's the key point. In our system, I'm essentially trying to do what my previous speaker did for matrix valued functions. So the evolution is, if you want, in the classical part, and the matrices are not touched. In particular, if they are not touched, the system is no longer ergodic, right? I mean, if you heard the word ergodic theory, being ergodic means you have a unique fixed point. So if you lose ergodicity, something goes wrong. And modified log Sobolev inequality is much more suitable to adapt for that, right? So this is my main advantage. It's better suited for non-ergodic systems. And my matrix valued inequalities, they have these non-ergodic parts built in. So that's actually where I come from, right? So anyway, mathematically, good. So complete modified logarithmic Sobolev inequality is, as you see, this is a variation we are modifying. I'm asking this to be true whenever I couple it with an arbitrary system. Now, why do I do that? one of the cool proofs of Talagrand when he proved these kind of things is he proved it for 2 points. He proved it's stable under taking tensor products, and then million of consequences eventually arose, right? So the problem is for these matrix valued functions, I cannot prove that number 3 is stable under tensor products. So I did what we do. I made it a definition to be stable under tensor products and just declared this, that's the only thing I care about. No? And now then you have to, you run into problems, and the problems are, find examples where it's true. So let me give some strengths and weaknesses. LSI inequalities are super well studied. My corrected notes include not only connection to concentration equality, Bakri-Emery, but also Ricci curvature, right? Ricci curvature is a super important tool to get these inequalities. Spin systems, the idea of having small system and putting them together has an enormous tradition in probability, really. I mean, Zegalinsky what mentioned, but I mean, Gross, Solov, Kostiakon, I mean, that is really super important. Now, LSI fails miserably for matrix valued functions. We had to accept that pretty early in the theory. This is how it started. It just doesn't work anymore. We tried, and by 2x2 matrices, there are now counterexamples where the constant should be 0. So we couldn't do it anymore. So that's why we went to LSI, MLSI. CLSI is, as I told you, by definition tensor stable. So that means you can couple it with a large system, you can combine them. So it's a good notion. I think we introduced that in a way, but anyway. And then until a couple of years ago, the only drawback is that there were only a few examples. Anything Gaussian, bosonic, fermionic works because it's Gaussian bosonic and you have some curvature condition. Then there are conditional expectation work. That's an example by Yvon Bardet. And up to a couple of years ago, that's it, right? I mean, there were no other tools to prove these inequalities. That has changed, as you will see, actually on the next slide. So, yeah, so I mentioned identity minus E. So, I mean, if you don't know what E is, just think of taking the trace or the expectation in the classical case, right? So if you have a commutative system, you just take the expectation onto constant functions. If you take identity minus E, that generates a semigroup. That's kind of how you have to. There's a translation between completely positive maps, and this is a generator of a semigroup, and that's a good one. There is some enormous work by Carlin and Maas who actually try to understand what are the right generators for this theory to work. I want you to leave it as this. We will come back to this. I just want to really point this out, that there's a major contribution which actually made this work. What is super interesting is that they use some inner products, which are extremely well known in operator algebras in the context of self-polar forms, or in the work of Afros and Lance about embedding von Neumann algebras into their pre-duals. So there are some norms, some inner products which you have to change if you go from commutative to non-commutative, which are well motivated from very different areas, right? So I just want to say there is something, the right thing to do, and we will look at this a little bit later. Connection to Wasserstein metrics, quantum, the reverse. So there's a lot of work going into that direction. Hypercontractivity and Wasserstein metrics are closely related. And I just want to mention this branch of authors. I should have mentioned all the co-authors, but anyway, what we proved a couple of years back, 2 years back, is that if you have a semigroup and you take L to the theta, which happens to also be a generator of a semigroup, if you need a good exercise, that's a good one. Then they all satisfy this inequality under some reasonable assumptions, some ultra-conductivity assumptions. So this means in particular, if you go to matrix algebras, the set of all generators which you want to consider in a certain class, dense. So it's not a singularity, right? I mean, this was expected, and since then we try to prove that this is true for every generator in matrix algebras, and that for an immediate step was to actually have a geometric version of Ricci curvature. I mean, we can prove that Ricci curvature implies this strong inequality. The only problem is that we have extremely few examples. If you start with even if you start with a graph with 5 vertices, to prove that this generator has Ricci curvature, it's just super hard. I mean, it's any notion of curvature, even for discrete graphs. So there's some problem with curvature and discrete. It clashes somewhere. And so it's a fantastic result if you have it, but it's not giving you this range of new examples which we were looking for. But it's good to know. Then there are transport inequalities which connect that too. Then this is breakthrough result by Gauer and Rosé, where they showed that all KMS symmetric. So there is this class of nice generators coming from Karl and Maass, and they all have the property now. So all finite dimensional systems have this complete property. And they gave estimates in terms of the spectral gap and the index. And my talk here is actually to improve some of these estimates. And then we have a different proof using geodesics. So there's some geometry. I strongly believe that geometry is relevant for this problem. And that's what this note here on the archive demonstrates. My main result is very simple to formulate. Complete return times implies CLSI, right? So return time, I will define what return time is, but if you have complete return time, the right notion of then you have the CLSI constant, and that direct path was not even known in the classical case. So we are, of course, you can say I'm defining something which you don't know, but this is the easy message, and I want to give you an example of that technique. So if you have a graph, you write down a generator by looking at the edges and nearest neighbors, right? I mean, this is a canonical graph on a commutative system. Now, since I'm looking at matrix valued function, this cannot be handled by the classical theory already, right? I mean, matrix valued function, f of p minus f of q makes perfectly sense. And what we prove as a corollary of our result is that the constant, the lambda CLSI of L, is bigger than the LSI constant over 1 plus log v. So that means if you use what my predecessors have studied, namely they know how to get good estimates for the log Sobolev constant, the classical, I mean, we're talking about the classical log Sobolev constant, then you get also estimates for the same object, but now with matrix valued functions. And the price you pay is log dimension. Now, if you're thinking of a quantum system, okay, so your V corresponds to the bounded operators of a Hilbert space of dimension D, bit, but then you take tensor product. So log V that's the log of the number of qubits. I think that's okay for many systems. The log of the number of qubits is good, right? I mean, that the number of qubits is good, but the log of the number of qubits, that's better, right? So yeah.
That complicated. Can you just explain what the things in it are, like P and?
Yeah, sure, absolutely. So I have a graph, 2 edges, and my function.
Board lights.
Hmm?
Turn on the board lights.
If I know it. Right, and I there are 2 edges here, right? And whenever I have an edge, right? So it's an your question is on the mark because I'm not really normalizing here, right? It's a function. F is a function from V into some matrix algebra. And f of p, my operator takes the difference over all the edges which connect it, right? It's a matrix valued version of the nearest Laplacian, nearest neighbor Laplacian, except for the normalization constant, which I don't care about. And so if I take this classical thing, and there are lots of results talking about LSI for that. Then for matrix valued function, I get the same. I can go from scalar functions to matrix valued functions, and I pay log v. Yeah.
Is this constant related to a spectral graph?
Do you see any spectral gap? So I have to ask you to wait for, yeah? Can you wait a little bit? So other key examples where that works beautifully is you start with a Lie group, take some subsystem of the Lie algebra, you define a corresponding differential operator on a Lie group, you do this for matrix valued functions, and that satisfies CLSI for matrix valued functions, and you get an estimate which works. If you now take arbitrary representations of a compact Lie group, since this principle works for matrix valued functions, we have a transfer principle. If it works for the original delta H, it works for the representation. So it's independent of the size of the representation. It's a uniform estimate. And this constant there is bigger than 0, right? It's not 0, it's uniformly bounded. The trick we do is we take the classical heat kernel estimates, which has been studied in analysis for years and years and years. It's not a trivial proof, but it's something we can just pay as a black box. And for these Hermander systems, these proofs are not trivial at all, but they're known. They're known for its Hermander, Pfefferman. There's a long traditional analysis, which gives me my input, right? So for this complete return time, this is known. And so I think I have to cut this short. If not, I'm going out of time. I just want to mention one thing. So if you take tensor product representations, what happens is that the typical representations have a fixed number of generators, right? So you can reformulate that in this fixed number of generators, which is independent of the size of the representation, right? So for instance, for SU2, you have 2 generators, and the representation is arbitrarily large. So that's why few directions, but many dimensions, and still you can regularize, right? You have decay to equilibrium. The decay to equilibrium is independent of the dimension of the representation, right? Good. I want to say 2 words about the proof. We define a quantity, the difference of entropies, dphi. This is like h of b minus h of a, if you like the symbolic notation. We prove an iteration lemma. So the relative entropy of phi star phi is smaller than d phi of x plus d of xy. Now I have to say that this idea is an idea of my former student, LaRacuente. The first time he came, he said, I want to iterate certain things. I thought he was crazy, plain crazy. And then we understood this. So this lemma here is improving on his first elementary lemma step by step. This final form. And this is not only a CPT map, that's a unital CPT map. So there's a U missing. So it doesn't work for all maps. But for this lemma, then we have a perturbation lemma. This was essentially done in Gao-Rosé. And here is the proof of the inequality. We are applying return time. What does it mean to be return time? We take a single channel now, right? It's not of the semigroup, a single map on matrices. We assume that some high power is order comparable with the conditional expectation onto the fixed points. And in this situation, there are good sets of fit points. Then we iterate this lemma. Well, we assume that this M is even and the thing is self-adjoint. We iterated M times, and we see that the relative entropy to the fixed points is dominated by this entropy difference at a constant M. We rewrite it and we get the inequality V1. So the proof is, this is 4 years and then 3-line proof. So it's But of course, the work is in the previous page. But so now it's really clear that if you have some power of your map being comparable with the worst case, voila, it works, right? I mean, you just have to have this comparison. So that's the proof, yeah? And then since I have a couple of minutes left, so this is here's the point. So I told you before, I need these completely positive unital maps, and they are not so interesting because in many cases you want to fix a certain density which is not the uniform density. So if you know that that's the case, and I was aware of that for a long time, but I dreaded that to say that out loud. But Karl and Maas, they said, okay, if you really want to fix or prepare a certain density, you have to adapt your generators accordingly. So I don't want you to read all of 0.1. I just want to believe Karl and Maas that they did it right. Yeah, so you need some modular condition and blah, 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 blah. So what I'm saying is that if we have this extra condition which allows you to prepare a ground state, or I think it's better to think of a thermal state, right? You have a thermal state which is your fixed point. You know how to choose this Lindbladian to create that thermal state as a fixed point. And the estimate which we had before, that complete return time implies CLSI, remains valid in this setting. That's all I'm saying. And now, Arthur, I come back to your question. If you use this trick, right? I mean, if you know return time implies CLSI, you can estimate the CLSI by the spectral gap and the logarithm of the dimension. But this is the wrong quantity. The thing you have to do is the logarithm of the Popper-Jones index. And my student, coming from von Neumann algebras, we wrote a paper on the Popper-Jones index in finite dimension. He went to Cambis-Rosé, they used that index to prove the result. Our improvement is in the logarithm, right? They proved it without the logarithm. Our new take to it with the logarithm. So that's the connection to the spectral gap, the logarithm of the index. And I think now, if you have a Hilbert space, you're going to the log of the number of qubits. We are finally getting to a more reasonable bound. Yeah, but the proof for this actually goes through some tricks which we learned from type 3 von Neumann algebras, right? So just to see that, there is a connection between tools from operator algebras. We use them in the finite dimensional setting. That is kind of an abuse. But if it works, I take everything. So here is the bad news. We try to apply this principle for representations of SU2. So we are really looking back at this array. For this array of electrons or photons, you have a natural SU2 action. You're going with one probability from the excited to the ground state. We have to go with a very tiny probability back. We write down all the generators, and then we hope to be able to prove that we have uniform bounds independent of the number of photons. And we failed. We tried. We failed. We tried. It doesn't work because the spectral gap is not uniformly bounded. We were not expecting this to happen. So the spectral gap for this new configuration is not stable. But the CLSI constant is only log n away from that spectral gap. So if you can actually calculate the spectral gap exactly, which we don't, but we know it grows with the number of qubits, then this works out. And just for I missed these slides don't have that. So, and actually, if you write this down in a fully von Neumann algebra setting, you realize that you have to work with semigroups, which really work on pseudo-differential operators and not only functions. And that sounds like, for some people this sounds scary, but if you do non-convex geometry, you know that you have to use pseudo-differential operators eventually. And here you don't have a choice because you're in a type 3-ish situation where you have to do it. So there's some connection to this geometry, on the back trail. Thank you.
Thank you. Any questions?
So if the logarithm.
Just one second.
I was just wondering if you know that the logarithmic loss is necessary.
No. No, I mean, the problem is that we have very few examples where we know that anything is necessary. Yeah, we don't.